Welcome
Yeah,
all.
live now. Yeah.
Right now, we are inaugurating the center. IMEI Cooperation Center is being inaugurated by Professor Gokarn. And following the inauguration, we would be having the technical talks today. So just now the center has got inaugurated. This is the center, Cooperation Center of Institution of Naval Architects and Institute of Marine Engineers, India. And welcome you all for who joined both online and offline for this inauguration, as well as the first technical session for today, this year, on 28th of January. In the spirit of cooperation, we have got two lectures today. One by Mr. Avinash Upadhye, and the second lecture by Mr. Arun Gupta. As the people who are in Mumbai and presenting or joining us physically as they settle down, we will start both the lectures. Today's chief guest for this session is Commodore Mathew, who is joining us online, and Professor R.P. Gokarn will be the session chair, whom we see is coming on stage. We have the president of INA, Mr. Das Gupta, Commodore Tatar, who is the Honorary General Secretary of IME, joining us from Mumbai physically.
So, Bhardwaj, am I visible now?
Yes, sir. Yes, sir. The chief guest has now joined us online, sir, for the session. The live streaming is happening. The chief guest, Commodore Mathew, has joined us online.
Sir, I think you have to request them to unmute the IME house because we can't hear what anybody is saying.
Yeah, we are on mute.
Yeah. Welcome, sir. The live streaming has started. Welcome to the joint session of INA and IMEI, as well as the inauguration of the INA-IMEI Cooperation Center today, where our new year 2023 has started on a very happy note, where with the collaboration of IMEI, we have started a center, as well as in the spirit of the cooperation. Today, we are organizing two lectures on behalf of INA and IMEI. With that, I would request the President of INA, Mr. Das Gupta, to start the sessions, please.
Thank you very much, Dr. VBS. Good evening, friends. This is a great occasion when two premier maritime professional bodies decide to come together to further the technical commercial advancement of shipping, shipbuilding, and allied sectors. Thanks to the tremendous goodwill of IMEI, led by Shri V.K. Jain, Shri A.K. Gupta, Shri Rajiv Nair, Shri Bhupesh Tatar, along with the teammates Mr. Mohan Pal Singh and Mr. Shetkar and the entire IMEI team. This initiative has been possible. We are missing some of them physically here, but we are sure they are with us in spirit. We are deeply honored to have Professor R.P. Gokarn, a leading light in maritime education, training, and research, to come and inaugurate the center. The areas of cooperation and the modalities of operation of the center's functions are being evolved. They will grow under the able leadership of younger generation. The scopes are huge, no doubt, in the changing world and challenging times. We together shall try to address the operational needs and the design and construction of appliances for the entire industry. We offer this as a homage to the younger generation, because of this land, we have just borrowed our time from their future for our limited existence. We hope the younger generation will come forward and ensure the success of this cooperation and this effort being undertaken by us. Thank you very much, and cheers.
Thank you, sir. The warm inaugural welcome. With the permission of the chairs, today we have got two lectures chaired by Professor Gokarn. It is my pleasure to introduce Professor Gokarn, who is the session chair today. We know him personally as a professor with long years of experience, who has probably trained all of us, or trained all the naval architects, or trained the naval architects who trained us. The formal introduction is this: Professor R.P. Gokarn obtained a degree in naval architecture from IIT Kharagpur in 1962 and a PhD in 1971. He joined the Department of Naval Architecture and Marine Engineering, which was later named as Ocean Engineering and Naval Architecture, at IIT Kharagpur in 1962 and retired in 2002. He has held positions of Professor, Head of Department, and Dean in IIT Kharagpur. After he retired, Professor Gokarn worked as a consultant for OERC Academy and was a visiting faculty member at the Indian Maritime University, Visakhapatnam. With this very brief introduction of Professor Gokarn, who will be chairing today's session, with the permission of the chair, I would also like to introduce the chief guest of today. Today's session, with the permission of the chair, I will introduce is Commodore K.E. Mathew. Commodore K.E. Mathew is an alumnus of Sainik School, Kadakuttam, graduated in Science from National Defence Academy, Karakwasala, Mechanical Engineering from Naval College of Engineering, Lonavala, Marine Engineering from Center for Marine Engineering Technology, INS Shivaji at Lonavala, and MTech from IIT Kanpur. He was a commissioned officer. He's a commissioned officer of the Indian Navy for more than 35 years. His rich afloat experience on various types of ships as engineer officer includes a landing ship, an offshore patrol vessel, and a destroyer. He also has varied industrial experience as manager, diesel engineer repairs at Naval Dockyard, Visakhapatnam, and as a manager, quality control, and chief administrator at Marine Gas Turbine Overhaul Center, that is INS Axila at Vizag. He has also been associated with ship equipment design at Defense Machinery Establishment, Secunderabad. As a technocrat, he has been the command engineering officer responsible for all matters pertaining to marine engineering at the Southern Naval Command, Kochi, and Eastern Naval Command, Visakhapatnam. On the human resource front, he has been the training officer for the naval cadets at training institutes, besides being an instructor at the Naval College of Engineering. Later, he has also been the director of naval training at Naval Headquarters. He has also held a diplomatic assignment as Naval and Defense Attaché at the Embassy of India, Ukraine in Kyiv. He has rich and varied exposure and experience in various facets of shipbuilding. He has been the Deputy Director General Quality Assurance at the Directorate of Quality Assurance, Warship Project and Warship Production Superintendent at Warship Overseeing Team, embedded with Mazagon Shipyards Limited. Currently, he is the Director of Shipbuilding at Hindustan Shipyard Limited. With this, we request Commodore Mathew to chair this session with the 2 lectures. With the permission of the chair, I would welcome the first lecturer of today. That is Mr. Avinash Upadhye. Mr. Avinash Upadhye today will be talking on the genesis, evolution, and future of integrated electric propulsion. Mr. Upadhye, it's my pleasure to introduce Mr. Upadhye. He is an alumni of National Defence Academy Kharagpur, mechanical engineering graduate from Naval College of Engineering, and Masters in Technology in Systems and Controls Engineering from IIT Bombay. During his naval career, he has served as Marine Engineering Officer on Indian Naval ship for 5 years. He has worked in the Naval Dockyard at Mumbai, undertaking repair, retrofitting of machinery controls, surveillance, and monitoring systems on ships and submarines. He has served in the Directorate of Marine Engineering in Ministry of Defence India, managing responsibilities of induction and life cycle management of machinery controls, instrumentation system, steering gears, ship stabilization system, and platform management system. He has served as a teaching faculty in Defence Institute of Advanced Technology, which is a deemed university in Pune, teaching controls and instrumentation to students of Masters in Technology programs, and conducted various professional orientation courses for marine engineering graduates on machinery control and instrumentation. Mr. Avinash has worked in the field of service support for Eastern origin military hardware from 2009 onwards, handling repairs, modernization, and product support for ships, submarines, and aircrafts. From 2014 onwards, at Larsen & Toubro, Mr. Avinash heads the business development in CIS region and East Europe for defense business. Currently, he is heading the international business development for defense and aerospace at L&T. Mr. Avinash is a fellow of Institution of Engineers. He has authored papers in IEA transactions on automatic controls titled Gamma Delta Approximations for Control Systems, and also authored specific standard documents for induction and acceptance of analog electrical instrumentation, resistance temperature detectors, thermocouples, Bourdon tube pressure gauges into the Indian Navy, and has presented various papers in National Conventions of Marine Engineers from 2002 to 2007. With this introduction and with the permission of the chair, I would request Mr. Avinash Upadhye on stage, please. Welcome, sir. Your presentation is visible, sir, to us who are joining online. So you can commence, sir.
Yes, sir. Very good afternoon. Respected Professor Gokarn, the session chairman, Commodore Mathew, Director of Shipbuilding, Hindustan Shipyard, Mr. Arun Gupta, elite guests of today's gathering, and the youngsters who are sitting here. Once again, a very good afternoon. It's really a privilege for me to present you a concept of all-electric propulsion, which has always been considered a very challenging concept. The problems start even with the loading of presentation, as you can see. In many ways, this particular moment is a sort of a deja vu for me, because I still remember about 20 years back, in one of the national conventions in Visakhapatnam, I was making a presentation about contemporary technologies in marine engineering on behalf of the Navy. Many technologies I presented over there. There was a podded propulsion, there was IPMS, and there was, of course, integrated electric propulsion. The interesting thing was, it was that time just an emerging concept. None of the warship had been commissioned. But 20 years from now, it's a long way, and we have something more to understand, learn about integrated electric propulsion. Now, perhaps even in the professional life, I can say that after having presented contemporary technologies and talking about all the integrated electric propulsion, even in the Indian Navy was constrained to induct this technology, and for various reasons, because this was not a proven technology, and Navy had programs which required Codoc propulsion. I hope you understand what I mean by Codoc propulsion. Codoc propulsion and Cogat propulsion, they had to go by that. And even in my personal life, I also moved away from the all-electric propulsion, and as the career took me in a bit different directions in different geographies. And
So I was more looking at something like sitting in Central Asia and CIS. I was more observing INSTC, International North-South Transportation Corridor. My next speaker would be a master on that particular subject and perhaps can explain that better. Now, recently I came back and after having come back, the subject has come back to me, and of course with a much more seriousness, because while Navy is now trying to make its way forward on the integrated electric propulsion, the industry is also working on a way how to contribute towards integrated electric propulsion. So that is where the first task came to me, that okay, how do you contribute? How do we go ahead? So this was a time that I looked back what has happened over the last 20 years. Because 20 years back there were multiple programs which were very popular program and everybody was looking at those programs. I had been monitoring various developments, new ships coming, but one thing was there, those famous programs were not there. So I really wanted to know what actually happened to those famous programs. There were different programs which became got commissioned and which really took name. So this was an exercise we carried to understand how integrated electric propulsion evolved over the last 20 years, from the concept to proving what were the lessons learned. And this I had sort of created an internal paper, a technology paper for us to have a white paper to way forward, which subsequently I converted to a formal paper. And today it's really an honor for me to share what views I had developed during the last few months while studying about visiting back the integrated electric propulsion. So,
yeah, so do you want to make it as a full screen, the PPT?
Yeah, you can just operate, it's okay.
Yeah, okay.
Yeah.
I'll try for full screen once. Yeah. Is it okay?
Yeah, perfect, sir. Go ahead.
Okay, thanks.
Well, to start with, you look at the governing factors for selection of propulsion system. What are these? Reliability, machinery space design, reduction and reversing ability, weight, volume, cost, auxiliaries, noise and vibration, etc. And once we look at these factors, we next look at what are the drivers which propel us towards choosing the electric propulsion over the other forms of the propulsion. The contemporary ships, especially the warships, require much higher onboard power generation for operation of more potent weapons and sensors. See, over the last 20 years, the way weaponry has evolved, the load of weapons on the warship is increasing and power generation requirement has been increasing. Plus, we have to bring down the consumption of the fossil fuels by maximizing the fuel efficiency of our prime movers. Further, we have to minimize our noise signatures by minimizing the mechanical components like gearing, and we have to respect the environmental regulations by minimizing the NOx emissions. And of course, those amongst us who are the designers are looking for flexibility in design of machinery space. This is exactly where electrical propulsion comes in. Electric propulsion technology changes the way a ship transmits power from the main engine prime mover to the propeller, and the way it manages and distributes electrical power to both the propulsion and non-propulsion loads. It does not change the primary source of the ship, power source of the ship, which remains the diesel engine, gas turbine, or the steam turbine. Coming to the genesis of electric propulsion. genesis of electric propulsion took place more than 100 years back. After the rather experimental applications of battery-driven electric propulsion at the end of 19th century in Russia, the electric propulsion for ships was developed in the United Kingdom, United States, and elsewhere. The US and UK based system competed against one another until 1920, when the British developed a lightweight, high efficiency mechanical drive system, which dominated ship propulsion technology. The US Navy revived the electrical propulsion technology during the World War II for destroyer escorts because during the World War II, their gear cutting capacity was falling short. The first electric propulsion for ice-going vessels was introduced around 1939, when the Finnish icebreaker SISU was delivered with a Watt-Leonard DC electric propulsion system. At that time, the high propulsion power demands could only be achieved by turbo-electric machinery. Steam turbine generators provided electrical power that was used to drive the synchronous electric motor on each of the screw shafts. The rotational speed was controlled by the electrical frequency of the generator. The generators would normally run one propulsion motor on one shaft, but there was also a possibility for feeding two propulsion motors from each generator for cruising at lower speeds. But later, with the introduction of high efficient and economically favorable diesel engine gas turbines in the middle of 20th century, the steam turbine technology and electrical propulsion more or less disappeared from merchant marine and naval vessels until 1980s. The development of variable speed electric drive, first by the AC-DC silicon control rectifier SCR in 1970s and the AC-AC converters in the early 1980s, enabled the power plant based electric propulsion system, which is typical for the second generation electric propulsion system. These solutions were majorly used in special vessels like survey ships, icebreakers, and other ocean-going vessels with dynamic positioning systems. In the Indian Navy, the electric propulsion was limited to about two ships. One was a survey ship called Darshan and one was a submarine depot ship called Amba. A typical propulsion and PGD plant comprised a number of generator sets feeding to the same network, supplying the propulsion as well as the hotel and auxiliary power. The propulsion control is done by speed control of the fixed pitch propeller. The typical elements which demarcate electric propulsion from conventional propulsion are the propulsion motors, the power converters, power management system, and in some cases, even the prime movers. I'll be focusing my talk subsequently on these four key technologies. In propulsion, we have options of podded propulsion and in-hull propulsion. Podded propulsion was introduced in early 1990s, where the electric motor is installed directly on the fixed pitch propeller in a submerged and rotatable pod. The rotating pod eliminates the requirement of steering gear. This concept was developed to enhance the performance of icebreakers and has additional benefits on hydrodynamic efficiency and maneuverability. Today, the podded propulsion or mermaid pods are widespread in cruise liner industry and in commercial shipping. Pods can be directly driven or indirectly driven. In a directly driven pod, the prime mover is located outside of the ship's hull within an enclosure or pod. This allows the propeller to be mounted directly to the prime mover, eliminating the need for an in-hull shaft. Indirectly driven propulsors, also known as azimuth thrusters, many of you would have heard shuttle, usually have the prime mover located inside the ship. In this configuration, a gearing mechanism connects the prime mover to the propulsor. The direct driven propulsors have a great advantage of lower noise level due to absence of any gearing. As far as in-hull propulsion is concerned, the prime mover is located inside the hull of the ship. Rotational torque is transferred to the propeller by using a shaft that extends from the motor and penetrates the hull of the ship. The propeller is connected to the end of the shaft and converts rotational torque into forward and reverse thrust. This method of propulsion requires additional equipment such as shaft bearing and bulkhead penetration, shaft seals at hull penetration, and rudders to provide steering control for the vessel. Although this method requires the use of shaft, significant reduction in shaft length is achieved due to flexibility in location of the motor and the propeller. This method is presently used in submarines and warships and in various navies across the globe. Electrical motors. The propulsion motors required for a warship can be of two types, AC motors or DC motors. There are various types of AC and DC motors that are available in propulsion industry. DC motors. DC motors are simple for installation and maintenance. They give high power and torque with fast response for starting, stopping, and acceleration, and are available in several standard voltages. However, DC motors require a significant amount of maintenance on their brushes, which deters their use in shipboard propulsion applications. One of the way out is the superconducting DC homopolar motors, or what is called SDCHM, in which the electrical polarity of the conductor and magnetic field does not change. This eliminates requirement of commutator, which makes these motors quieter, though slip rings are still needed. Homopolar motors are attractive for potential use in direct electric drives for ships because of their compactness and high power density. First homopolar motor for naval application was successfully demonstrated on the test craft Jupiter 2 of US Navy. The US Navy has been researching on the SDCHM ever since 1960s. On the other hand, the AC motors are highly durable with longer lifespans. There are two types of AC motors which are considered for warship propulsion. These are permanent magnet synchronous motors, or what we call PMSM, and advanced induction motors, AIM. The permanent magnet synchronous motors are widely used in commercial shipping, large auxiliary ships, and cruise liners. The PMSM has received favorable consideration as a ship propulsion motor because of its power density and quiet operation. These are majorly used in mermaid pods also. For in-hull propulsion, requirements of warship especially, PMSM motor technology is still evolving, and the advanced induction motors are the ones which are most employed. The simple and rugged construction of induction motors contributes to its reliability and makes it attractive for shipboard propulsion applications. Advanced induction motor has been evolving over the past very many years. It was primarily developed for applications where low speed and high torques are required, such as ship drive. Major advantage of advanced induction motors are over the permanent magnet motors are high power density and optimum cooling. In advanced induction motors, we can achieve signature reduction also by selection of appropriate number of stator and rotor slots, poles and faces, and this adds to the robustness and the low cost also. Next important element is power converters for controlling the propulsion motor. The electrical motors used in propulsion require power conversion and control equipment to provide effective speed control. An ideal converter for marine propulsion applications needs to be engineered for simplicity, reliability, ruggedness, and provide graceful degradation in output in case of any failure. The converters also need to include circuitry to provide the best waveform fidelity for acoustic performance. They must have convenient monitoring for diagnostics and troubleshooting, minimize source and load harmonics, be immune to problems with electromagnetic interference and cooling, be modular to expedite maintenance and repair, and minimize the cost. The technological advances in power electronic devices are a major factor in power converter technology. The requirement for high-powered semiconductor devices include high blocking voltages, low leakage current, and high switching frequencies with low conduction drops and losses. Various propulsion converters which are available are cycloconverter, synchroconverter, pulse frequency modulation, and pulse width modulation. The pulse width modulation converter is most suitable converter for controlling the speed. The PWM converter has higher, more constant power factor for better efficiency, constant harmonic frequencies to ease any supply filtering required, and smaller size and weight. Next comes the integrated power system. In all the electrical ships, the power supply is to the tune of at least 4 kV. And the later ones which we have, the carrier, they have a power supply to the tune of 11 kV. So there is always a high power supply which we are managing, and there is a low power supply which we are managing. And also we are managing various loads. So this is where the importance of the integrated power system or IPS comes. The integrated electrical propulsion system on board ship essentially requires integrated power system, which will provide electrical power for propulsion, weapons, and ship services. IPS provides electrical power to ship service load and electric propulsion for a wide range of ship applications, including surface combatants, aircraft carriers, amphibious ships, auxiliary ships.
So shall I move the slides for you?
Sorry.
This one?
Yeah. I didn't want to put a slide, so just say power map. The IPS should be able to rapidly reconfigure the electrical distribution system in the event of a combat equipment casualty. The IPS architecture integrates the power generation, power distribution, storage, and conversion of electrical power for both ship service and electrical propulsion loads. The integration process uses methodical system for developing tailored configuration for the range of ship applications. Evolution of modern day electric ships started with SS Queen Elizabeth II in 1987 and was followed up with multiple realization of integrated electric propulsion, which included cruise liners, tankers, LPDs, aircraft carriers, and destroyers. These are some other implementations which were done across the world. While various key technologies could be successfully implemented on most of the ships, on destroyers, realization of integrated electric propulsion has been a full of burning, the hand burning, or what we can call an enigma. While all technologies were successfully proven, but when they were integrated on a destroyer, the concept did not live up to its expectations. Perhaps only UK Navy and US Navy have ventured into an electrical propulsion for destroyers. I'll briefly touch upon two examples. First, the Type 45 destroyers. UK Navy Type 45 destroyer program. Unlike cruiser, carriers, tankers, or LPDs, destroyer has a displacement of only about 7,000 tons. It has a power to weight displacement ratio very high. For large ships, we require, large ships such as tankers and aircraft carriers, we require about 0.5 megawatt power for 1,000 tons. But on a destroyer, we require about 5.5 megawatt for 1,000 tons, which is nearly 10 times higher. There are steep variations in powering requirements during cruise conditions and maneuvering conditions. While at economic cruising condition of 6 knots, destroyer requires barely 15 to 20 megawatt of power. It requires about 50% powering to generate a speed of 24 knots, and at maximum power of around 30 knots, 30 plus knots, it goes for a full power. In an integrated electric propulsion, power management system has to also withstand and be able to manage the load transient. Like if the ship is maneuvering and has to move from say 20% loading to the full load and back, it is not merely the prime movers which have to continuously manage the fluctuations of the load. The switchboards, the power management system, all of them have to absorb these fluctuations. The realization of integrated electric propulsion on a destroyer necessitated further technological advancement such as propeller motor drive capable of providing 20 to 25 megawatt power, high voltage management system for 4000 volts, power electronic capable of managing the complex load management requirements on destroyers, and provision of high power density prime movers which could provide fuel economy over a powering rating from 10 megawatt to 60 megawatt. There are four major developments which took place specifically for realization of Type 45 destroyers. The advanced induction motor, capable of delivering 20 megawatt power at 165 RPM, was developed by GETC for powering of T-45 destroyers and was planned based on, and the powering of T was planned based on two such motors. These motors, unlike normal motors, are 15-phase supply motors having 3 channels of 5-phase each. So you can understand the complexity of the motor itself. With the motor comes the power converter. The medium to 25,000 power converter. This was also developed by GETC first time for the T-45 destroyers. These provide about 40 megawatt of power, highly dense power, without use of heavy and bulky transformers or gearboxes. So that's a conventional. You have a converter where you have a conventional motors are there, but here the entire 40 megawatt power is being converted with the semiconductors. Next comes the prime mover. On Type 45 destroyer, configuration of IET has two specially developed WR21 gas turbines of 21.5 megawatt. Besides, 2 in number 2 megawatt diesel alternators feeding into a common bus bar. As we know, diesel engines cannot meet the powering requirement of destroyers, and simple gas turbines have a major drawback of poor part load efficiency. So on the left, you can see the basically the specific fuel consumption curve, and on the right side, I have given this intercooler and reheater cycle of the gas turbine, which was specifically developed for the Type 45 destroyers. This gas turbine called WR21 was developed by Rolls-Royce, and this is a complex gas turbine. It incorporates compressor. If you see after the compressor, there is an intercooler and there is a reheater with a waste heat recovery. Development of WR21 ICR gas turbine was linked to Type 45 program. As a matter of fact, as the development of turbine GT got delayed, the program also got delayed. As we can see from the figure, the ICR GT reaches a flat specific fuel consumption from 7,000 horsepower onward, which is far lower than the simple cycle gas turbines such as LM2500. The ICR gas turbine thus became one of the most key technologies for realization of integrated electric propulsion. Management of high voltage and proving the power management system functionalities. A special de-risking program to prove all technologies was set up. It was called Electric Ship Technology Demonstrator. The principal objective of the Electric Ship Technology Demonstrator, or ESTD, it was called, was setting up configuration and proving a fully marinized integrated power system in a combat act, high voltage transformer less propulsion, application of dynamic braking resistors, first application of General Electric advanced induction motor, and Rolls-Royce WR21 gas turbine. All technologies were going for the first time, so therefore they had to be tested in a shore-based facility to prove the concept. Validation of complex electrical system models, proving load shedding and schedules during the failure event, translation of land-based power system protection to the more demanding naval environment, testing the fault tolerance and robustness of the various electrical systems on board, derivation of logic behind load sharing between various load generation components. Despite so much of effort which was put in, what was the actual experience? Despite the staggering investments made in testing out electrical propulsion in ESTD, the actual experience of Type 45 destroyers was very different. Due to delay in program execution, the test results were not available for first 5 ships. Therefore, the problems arising in operation could not be mitigated. Despite best of the efforts, ESTD could not realistically simulate the complex scenarios at sea. Ships suffered with reduced power availability. The power management system on board ships could not manage the loadings at higher tropical temperatures. The problems surfaced multiplied as these ships came closer to the equator in the tropical waters. The gas turbines and diesels, like on a particular plant, there were 2 different gas turbines and 2 diesels, and they were expected to have a certain characteristic at the higher temperature. But none of these propulsor prime movers had a consistent characteristic. All the gas turbines had a different characteristics, had a different load power generation ability at a higher temperature, and same happened with the diesel engine. So problem came to the power management system, which could not sustain these problems. And as a result, when the load fluctuation could not be sustained, at the time of maneuvering, the gas turbines failed constantly, leading to major propulsion failure, major power failure. Perhaps the Type 45 ships suffered more than 5,000 major propulsion failures in 5 years. So you can imagine the gravity of the problem which took place. This is the statistical data on major failures which were presented by the UK MOD to the UK Parliament. Special rectification power plant improvement project was thereafter taken up at a cost of 211 billion sterling pounds. Under this program, the 2 in number 2 megawatt Wärtsilä DS were removed and are being replaced by 3 in numbers MTU 4000 3 megawatt generator. Now this program is still going on. 2 ships have already been done. 4 ships are yet to go. The program, which was there for construction of 12 ships, was curtailed to 6 ships. It was realized that hybrid propulsion like Podlock or Podlock could only handle the requirements of destroyers and frigates. UK Navy had earlier successfully realized Type 23 frigate program with Podlock propulsion. Therefore, for the next generation frigates, that is the Type 26 program, they again switched back from the integrated electric propulsion to the Podlock propulsion. And further, another program was announced, that was the Type 31 program. This program they have announced with the Podlock propulsion. Other European navies who had separated themselves from all electric destroyer program. Earlier, when this integrated electric propulsion program started, that is toward the late 90s, there were all European NATO navies were together in the program. Around 2000-2001, that is the time the French Navy, Italian Navy, they realized that okay, we cannot make it. This program is not viable. The costs are shooting. They had already separated themselves from this program, and that is how UK Navy went for Type 45 program separately. And the European Navy, they decided to stick to a safer option. They went for the Podlock or Podlock propulsion. These are the programs which are executed by the European Navy. Now coming to the US Navy. In US, everything is big. All parameters are big. All specifications are big. They had planned as many as 32 in number destroyers under a DDG program. And the displacement of a destroyer was 15,000 tons, which is something not a normal. Destroyer is normal 7,000 tons, but for them, the destroyer was also 15,000 tons. Integrated electric propulsion and new generation weapons were planned on these destroyers. That is what we hear the direct energy weapons and electromagnetic ray guns, which has yet to come in the other navies, were planned by the US Navy, and these required a very high power output. Having taken lessons from the UK Navy's Type 45 program, US Navy opted for a safer option of high power but simple cycle gas turbines. So they did not go for the WR-21 program, which was gas turbine which Rolls-Royce had specifically developed for the Type 45 destroyer. The total power generation capacity of DDG 1000 ship is to the tune of 78 megawatt. You compare with Type 45 destroyer, where it was a 47 megawatt, which is 78 megawatt. They also had a shore test facility set up, and the cost of this shore test facility was set up in Philadelphia is the tune of 10 billion USD. In Indian Navy, we complete 2 programs in 10 billion USD. Now, despite all these investments, the DDG 1000 destroyers also could not come up to the expectation. The power generation of 78 megawatt at medium voltage of 4160 resulted in higher power losses. You compare, Type 45 also had a 4000 voltage, 47 megawatt, and these guys, these people went for a 78 with 78 megawatt, still had 4000 volt. They could have gone for 11 kV. But as a result, what happened? The power losses were much. To avoid short circuit failure, what they did in the US DDG, normally on a integrated electric propulsion, it's an island. All the generators, they feed a common bus bar. But what they wanted to prevent that, so they decided that they will not couple the 2 switchboards. And there was a separation between the port and starboard of the power supply, which is actually, if you speaking, is not a truly integrated electric propulsion. But for the preventing the short circuits, or they went for this particular concept. But what happened in the process? When they were cruising, when that ship cruises even at a say 16 knots, it has to run a prime mover on both the sides. So it has to run a higher capacity gas turbine also, and it has to run lower capacity gas turbine also. And both the gas turbines operate barely at about a 20% efficiency. And as a result, the fuel consumption was very high, and the operating cost of the type DDG 1000 destroyer has been phenomenal. So how it happened in US Navy, once again, in case of US Navy, also this program, the dissection was done and it went right up to US Congress. And then it was decided that instead of 32 ships, they said, let's have only 3 ships. The program was struck down at only 3 ships. Instead, the US Navy said, okay, we would like to go for another 68 destroyer with a Kogak propulsion. They went back to the old reliable option. The Indian Navy has been watching the development in electric propulsion around the world to maintain contemporary level. Lessons from Type 45 and DDG 1000 destroyer programs have been discouraging. The lesson learned has been clear that IAP can be very well be realized on the aircraft carrier, LPDs, but not on new generation destroyers class ships which are being planned by the Indian Navy. These ships would have challenging loading regimes requiring delicate balance between the full power and cruise economy. UK Navy followed up on the lessons learned on Type 45 destroyer with successful realization of Queen Elizabeth class carriers. But as compared to this destroyer, the Queen Elizabeth class aircraft carrier of UK Navy is a 65,000 ton ship. And on this ship, integrated electrical propulsion has been successfully been proven. And again, the operating voltage on this ship is 11 kV instead of the 4 kV which was there on the destroyers. Therefore, we can replicate the proven concept of Queen Elizabeth class on India's 3rd aircraft carrier program. For destroyers, class ships, the concept of IEP, as I said, has not been successful in both US and UK Navy. The program cost for development, re-engineering, and operation scaled dramatic limits. These got reviewed at the highest level in US Congress and UK Parliament respectively. The result of this review was truncation of both programs. The other NATO navies which had joined the IAP program earlier separated themselves from the program and opted for Code-Lock and Code-Lag propulsion with Frame class frigates. UK Navy, who had pioneered with Code-Lag with Type 23 class frigates and is now continuing with Code-Lag on Type 26, but on announcement of Type 31 frigate decided Kodak propulsion which shows a crack in their earlier resolve to have only electric ships. Our Indian budgets do not permit us to engage in R&D and proving of indigenous electric propulsion, integrated electric propulsion through a technology demonstrator in the manner that these two countries have pursued. ESTD program was started by UK Navy in the year 2000. However, the program through ESTD could only go on one Type 45 ship. The program started in 2000, ESTD was established, the ship construction also started. As the ship construction went on, the results of the technology demonstrator was not available, and due to the construction of the ship, the pressure for the shipbuilding, the first 5 ships were commissioned with unproven equipment, and the equipment which actually got proven in the technology demonstration went only on the 6th ship. So it was only the 6th ship which was quite, that is Duncan, which was quite stable. In order to realize the cost-intensive program like IEP in India, it is imperative that the program executed within the Indian ecosystem of R&D industry. Why I say Indian ecosystem? Because like NASA has also got a space program, but we launched the same satellite at a fraction of the cost. So similarly, it is better that we conduct this program in our own ecosystem, with our own R&D. The Indian R&D and industry have evolved over the last 2 years. The government has recently made 2 path-breaking announcements to facilitate 25% R&D budget allocation to private industry and provision of forming special purpose vehicles (SPVs) between DRDO and industry for research programs. Both these provisions can facilitate setting up of R&D structure for development of integrated electric propulsion on the lines of Cmde establishment, which was created for developing submarines. Infusion of the DRDO industry partnership will impart effectiveness to the structure and enable time-bound execution of the program. The setup can undertake activities starting from basic and detailed designing needed for integrated electric propulsion configuration required to meet the ship's requirement, propulsion system integration, power generation, prime movers, propulsion motor, shafting and propeller, high voltage and low voltage switchboards, power electronics, high voltage power distribution system, ships design, safety design for management of high voltage power distribution. In conclusion, we can say that integrated electric propulsion is the need of the emerging time, and India needs to start in this direction. We can draw lessons from Type 45 and DDG program and attempt to implement these concepts in the new generation programs. Over the last 2 decades, we have learned that integrated electric propulsion is suitable for the aircraft carrier. We have an aircraft carrier plan, we can implement on that, and similarly we have LPDs which are being planned, so we can plan IEP on the LPD. The R&D setup can be created under the framework of DRDO industry partnership, and the Indian industrial ecosystem is capable of realizing this integrated electric propulsion into the functional reality for future Indian naval ships. While concluding, I'll just say one thing. Like I said, 20 years back, I was the first time I spoke about integrated electric propulsion, and I had a slight kind of a thought. I said, I'm 20 years later, I'm again talking about integrated propulsion, but we don't have an implementation in India. But when you read the paper, you say, I felt like saying one thing, thank God we did not enter earlier and did not burn our finger. Perhaps now is the right time we can get into integrated electric propulsion. Thank you very much. Any questions? I'm ready.
There are a few questions, sir, with the permission of the session chair and the chairman. There are a few questions which have come in the QA box. So I would request the session chair to come and the permission of the session chair. I'll just read the first. Yeah. Can I read the first question, sir? Yeah. The first question which is asked online is, How are the emission levels of the gas turbine prime movers managed?
How about emission?
How are the emission levels?
Yeah, and Dr. Iyengar, we also have Mr. Pai on the call. So if he wants to clarify himself, that also we can do based on
Please, you can just,
permission.
he has those 3 questions, so you can just probably.
Compared to between the gas turbine and diesels, the diesels have been a larger problem. But again, when it comes to the gas turbine, yes, emission levels are better than the diesel. But yes, we have to handle the low loads.
Mr.
It is
Pai,
very important that the gas turbine, that is why the powering of the rating of gas turbines is very, very important. That at what rating, what is the denomination of rating which you select for the gas turbine, so that the idea behind the integrated electric propulsion is that it's a constant frequency. The power generation is a constant frequency, constant RPM power generation. So the machinery should be operated at the optimal power, and loading and unloading, that is taking on and taking off the prime movers, should take place by the power manager.
Sir, I would request Mr. Pai, who has just come to the panel, to ask his other 2 questions, sir. He has also have 2 other questions. So, Mr. Pai, if you can.
Yeah, can I be heard, sir?
Yeah, you're heard. So you can just please ask you 2 other
okay. Well, first of all, let me apologize because I am speaking from the perception of the commercial industry and not the Navy. And I know that the primary objective in the Navy is strategy and defense. Whereas in the commercial sector, we are looking more at other issues like specific fuel consumption and so forth. That was the basis of my question with regarding these pollution levels, because as you would know, we are governed by IMO regulations, whereas I think these do not apply to the Navy. So apologies for the question, but I don't know how the Navy addresses these issues.
See, this is the challenge for the Navy. In case of like the integrated electric propulsion applications, implementation on the cruise liners, now it is there in the cargo ships, they have been very successful, because if you see the powering loading regime is always well defined for the commercial ships. So you are operating all your gas turbines. Like in case of RMS, it's the gas turbines only, the only gas turbine, and all the cruise ships, they're also having gas turbines with the power generation by gas turbine, but they are operating at an optimum power. So this problem gets tackled at a design level. It's because of the operational philosophy of these vessels.
Yeah, the question that follows from this is that do you address the issue of specific fuel consumption on gas turbines?
See, the issue of specific fuel consumption for the commercial ships.
No, I'm talking of the naval ships. Is this an issue that has to be reckoned when you're doing the design for naval propulsion?
See, this is where if you see both the implementation. Now, if you see again, gas turbines are there, IMT gas turbines are there on the aircraft carrier. Again, aircraft carrier, the operation is a stable operation. There is no fluctuation. But the problems which happen is on the destroyer, where you move, your power regime moves from say 6,000, from 7,000 megawatt, 6,000 to 16,000 at any time to 60,000 megawatt. So what happened here? What UK Navy went for? They said that let us have a gas turbine which can manage these load fluctuations. The WR21 gas turbine with an intercooler and reheater. That is basically a gas turbine. That's a complex cycle gas turbine, and that had a fuel consumption curve which was a flat, like a diesel engine. And from 7,000 megawatt onward, it could give a good low fuel consumption. But unfortunately, what happened on this particular, and this was implemented on Type 45 destroyer, the intercoolers were not stable. The intercoolers used to fail in the tropical climate. And when the intercooler used to fail, whenever the loading unloading would take place, the gas turbine could not come down to the low power, they would simply trip. So the problem became much worse for the destroyer. So that is better handled by the podlock or podlock propulsion. So code life and code law propulsion, you are engaging or disengaging your prime mover based on the power requirement. So there you go for electrical power generation. The electrical power generation is linked to the diesel power generation. So that is a cruise. At a cruise mode, it's only you are using the gas turbine when you are going into the high power mode. So that is how the Navy has to manage, and that is how even UK Navy with the Type 26 has come back to code law propulsion. European navies have also switched back to the means they never went to the other propulsion. They are sticking to that. So it is a code law and code law propulsion, which is like a which gives a balance which is required in frigates and destroyers.
One more question on this. What is the exhaust gas exit temperature at the funnel of this cogeneration gas turbines?
On intercooler base?
No, at the funnel I'm talking about, the exit temperature from the ship.
See, after the all cooling, because there is a cooling system is there, it is brought down below 600 degrees centigrade.
Sorry, how much is it?
600.
600 Celsius, right?
Yeah.
So you don't try and absorb some of this energy in the exhaust gas system?
No, see, this is exactly what ICR gas turbine is doing. If you see ICR, I can show that cycle again. In that, the reheater which is there, that is after the second stage compressor, the air goes to the exhaust. It takes the heat from the exhaust and then it gets preheated and then goes to the combustion chamber. So in that gas turbine, this was attempted.
Okay. Thank you, sir.
So I would request Mr. Khalgatki has also asked a question. So he has come online. So I just request him to pose his question, sir.
Yes, Mike. Before I raise the question, I compliment the speaker for his presentation on electric propulsion. Though electric propulsion is not new, it's quite age-old, and it has been used extensively. Perhaps from Navy point of view, it may be a new venture. So from that point of view, I don't add anything further. But I do know that the harmonics has its own way of posing the problems. So how does the integrated electric propulsion designed to take care of these harmonics, which can be really problematic during the operation? Because both the pulse width modulation and other modulation, there are two frequency modulation. Which one is more preferred? Because both has pros and cons. So how does that has been addressed? Perhaps a line or two would be appreciated from the speakers.
Yeah. The pulse width modulation is preferred over the pulse frequency modulation. And basically coming to the harmonics, that is where you have the converter, the design of the entire VDM to 25000 power converter is based on pulse width modulation.
Okay, thank you, Mr. Khalgati. So we have next is Dr. M.K. Ghosh Roy, who is on the call. Sir, if you want to post your question to the speaker. Yeah, Dr. Ghosh Roy, you can ask your question. I think Dr. Roy is not able to speak. Dr. Anger, if you want to post a question to the
speaker. I'll just read his question. Dr. Ghosh Roy wants to know whether IAP is justified by economic viability.
IAP is a high installation cost, but when you come to the running cost, implementation is done, the running cost comes down.
Yeah.
As a matter of fact, when IEP failed in case of DDX 1000 program, is basically because they did not look at the running cost and find that the running cost has become unmanageable.
Dr. Ghoshroy, are you online and would you like to?
Yes.
Actually, the running cost has been the major criteria for IEP. That is how we get all the prime movers of and with a different denomination of power into feeding into a common bus, so that we can, as per the load requirement, we can offload the prime movers and only use prime movers at rest of the